So in the first three sections, we looked at Laplace transforms, which were a way of, it's basically an operator that allows us to handle integration without actually having to solve an integral. It just transforms from one function to the uh, antiderivative of another function. So just like with derivatives and integrals, sometimes we go in one direction, sometimes we have to go in the other direction. If we transformed a function or a differential equation using a Laplace transform and we simplified it and we rewrote it, at some point we would want to go back to our original domain, our original variables. So we would have to inverse and go backwards. So I have a list of the different um, transforms that we've done. So these are going from f of t to the Laplace transform of f. Same thing here. These are functions of t going to the Laplace transform of f. And if we're going in the other direction, then we're looking for the inverse Laplace transform of f of s. So normally we transform little f into big F is often the notation we use. So in this case, we're transforming from the big F of s back into little f of t. So we just use the inverse notation, and we're just going from the right side to the left side. So the book goes through a few examples, and they talk about how there are occasionally two different transforms, but the only difference between the two transforms is that one will be continuous, one might be discontinuous, and they will agree all except at that point of discontinuity. So essentially, there's just one continuous function that is a solution to this inverse. So what we're going to focus on is how do we actually do these inverses? So let's work through several examples, and hopefully that'll get you going in the direction you need to go. So if we have 2s squared plus 4, let's transform it back to f of t. So let's do the inverse Laplace transform of that particular function. So if we look back at our list, one of our lists has a constant on top, s squared, plus a constant squared on bottom. One has s on top, s squared, and a constant squared on bottom. If we look at this one, this is 2 squared. So essentially what we have is b on top, s squared plus b squared on bottom, where 2 is b. 2 is b. So if the transform of sine goes into that, then the inverse transform of this goes back to sine of bt. So this goes to sine of bt, where in our case b is 2. So in other words, this is the function whose Laplace transform would give us that. So similar idea to when we learned how to do antiderivatives, except we're just basically doing an anti-transform, an inverse transform. Suppose that we had this. So in this case, if this is going to be s squared and b squared, then b would be 3. Well, we don't have a 3 on top. So what we can do is we can put a 3 on top and divide by 3 out front, and we don't need that 4, so we can bring it out front. So we could rewrite this as 4/3 times 3 over s squared plus 9. And when we transform that back, we have 4/3. The transform of b over s squared plus b squared we saw was sine of bt, where b in this case is 3. So we're just going backwards, and just like with antiderivatives, sometimes we have to make a fit. We know what the formula is. We know that the formula has a constant on top and that same constant squared on bottom. So the constant we had is not the one we need. We just need to make a fit. So let's look at how about 3 over s plus 2 cubed. So let's compare this with what if we had 3 over s cubed. So what transforms into having an s cubed on bottom? If we go back and look at, and I'm not going to flip back every time, I'm going to look at the ones in my book. N factorial over s to the n plus 1, so s to a power, that comes from transforming t to the n. So if we transform t to a power, this is how we do that. So if that's the case, in this exponent here is n plus 1. So that means n is 2. So we should have 2 factorial on top. So we can do this several ways. We could put a 2 factorial on top and divide by 2 factorial out here. So we don't need this 3, so it would come out front. So just doing this one, we would have 3 over 2 factorial, which is just 2, times 2 factorial over s cubed. So 2 factorial s to the third. The inverse Laplace of that would be 3/2 times t to the n, and in our case, t is 2. The thing that differs between what we just did and this one is that instead of having just s cubed, we have s plus 2. But remember where that plus 2 is, that's a translation. And remember what causes a translation. E to the at causes the translation of s minus a. So what number is being subtracted from s here? S plus 2 equals s minus a. So essentially, what would that make a? If we subtract s's from both sides, those cancel. If we take the opposite, a is going to be negative 2. So this has been translated 2 units in the negative direction by an e to the at. So we need an e to the negative 2t. If there was no translation here, we would have no e. But since there is translation, since we have a number added or subtracted from s, we have to figure out what a is in s minus a, and we do e to the at. All right, what about, how about we do 1 over s squared plus 4s plus 8. So on this one, this doesn't really match any of our classic formulas. Our formulas have either s squareds and b squareds or s minus a squareds plus b squareds on the bottom. This isn't either one of those. So what we need to do is we need to take the s squared plus 4s, and we need to complete the square with that. So if we complete the square, we take half of the 4, which is 2, and square it. So 4. If we add 4 on bottom, we also have to subtract 4 to keep it equal. So that's equivalent to 1 over s squared plus 4s plus 4 factors to s plus 2 squared. 8 minus 4 is 4. So that's s minus a, and that's b squared. So notice we don't have an s on top, so that's not going to be of the form that has, let's see, where is it? S, so we're not going to transform back into cosine because we don't have an s on top. So since we just have a number on top, then we're going to go back to b s minus a squared plus b squared. So we need to have b on top. Well, b in our case is 2. So to make it fit, we need to pick up a 2 on top, which if we pick up a 2 on top, we have to pick up a 2 on bottom out front. So we have 1/2 times 1 over s plus 2 squared plus 4, or we could call that 2 squared. So that's, I've left my 2 off. We have a 2 there. We picked up a 2 on bottom and on top. So we have b s minus a plus b squared. So a in this case is -2 again. S minus -2 makes s plus 2. So transform that. 1/2 is the constant. If we're doing b, then b over s squared b squared, then that's the one that's sine of bt. And if we have an a, it's e to the a t. If we don't have an a, if it's just s to a power and not s plus or minus a number to a power, then we don't have this e. But if we have an a, we have this e to the a power. Okay, how about this one? Is that what I want to do? No, let's not do that one. Let's do this one. 3s minus 15 over 2s squared minus 4s plus 10. So one thing we could do is every term on bottom has a 2 in it. So we can factor a 2 out, and we have 3s minus 15. If we factor a 2 out on bottom, we're left with s squared minus 2s plus 5. So when we get to this point, we need to complete the square on bottom. So half of -2 is -1. Square it is 1. So if we add 1 there, we have to take away 1 there. So that makes 1/2 of 3s minus 15. S squared minus 2s plus 1 makes s minus 1 squared. If we factor those three, when we take the 1 that we picked up, had to come from somewhere, so it came away from that 5, so that gave us 4 there. So we make the bottom an s minus a squared plus b squared, but the top doesn't look anything like that. So what do we do with the top? We need the top to possibly have, the top needs to have either an s minus 1 or it needs to have a 2. It doesn't have either one of those directly. If we factor a 3 out on top, we'd have an s minus 5, not an s minus 1. So what we want to do is, it's not exactly like partial fraction decomposition, but we want to rewrite that fraction to have some quantity of s minus 1s on top and some quantities of 2. Because if we have a 2 over that, we have a b over s squared plus b squared. We know what that goes into. If we have an s minus 1 on top, we know what that goes into. We have a formula for that particular inverse Laplace. So we want to see, can we write this fraction in terms of so many s minus 1s, so many 2s. Let me erase this here. So for these two fractions to be equal, the denominators are the same, so we would want to make the numerators equal. So how is 3s minus 15 going to be some s minus 1s and some 2s? If we distribute the right, we have a times s minus a times 1 plus 2b equals 3s minus 15. So this is the only s term on the right. This is the s term on the left. So for the right side and the left side to be equal, they have to have the same amount of s's. So 3s and as, so a would have to be 3. This is a constant on the right. It has no s's. This is a constant on the left. So negative 15 and 2b minus a, those have to be equivalent. So we know what we got for a. A is 3. So if we add 3 to both sides, we get negative 12 equals 2b. Divide both sides by 2, and we get b is negative 6. So for our fraction, we're going to have 3 s minus 1s, and we're going to have minus 6 2s. B is minus 6, that's going to be 2.5. And that's over s minus 1 squared plus 2 squared. So in our transformations, we either want an s minus 1 on top or we want a 2 on top. We don't want both of them on top. So what we can do is we can split this into two different fractions. We can, for the first one, we can pull the 3 out front, and we can call that s minus 1 over s minus 1 squared plus 2 squared. For the second one, we can pull the minus 6 out front, and we can call that 2 over s minus 1 squared plus 2 squared. So each of these can be transformed now. We have a 1/2 out front. For the first one, we have 3 times. If this was just s over s squared plus 2 squared, what would that be? Is that cosine? Yes, if we have s over s squared plus b squared, that goes back to cosine bt. So this one goes back to, whoops, cosine b, which is 2t. This 1 is our a, so e to the a1t. And then for this one, we have minus 6 times, this was basically a b over s squared plus b squared. That goes back into sine bt. A is 1, so e to the 1t. So the s minus 1, that's where we got the e to the t from, because we had that translation. We had the s minus 1, so our variable on top, so cosine here, constant on top, so sine here. We could distribute the 1/2 if we wanted to, or we could factor the e to the t's out front. So either way, that's fine there. Now, on some of our problems, we might have something where we had, let's say, an s minus 1, s plus 1 on bottom. Or we might call it, before we got to that point, an x squared minus 1. Well, we have a formula for x squared plus b squared, but we don't have a formula for s squared minus b squared. So, well, what will we do there? So what we could do, and to make this easier, let's pick a different number for the top. Let's call it 4. If we wanted to do this transform, and we don't have a formula for this, keep in mind that we can break this down into different fractions. We can do partial fraction decomposition where whatever factors we have in this denominator, we can break this fraction into different fractions using each of those factors on bottom. And remember the way that works. To find out what our numerators have to be, we reassemble the right side. So the first fraction would have to pick up an s plus 1 on top and bottom. The second fraction, to get the common denominator, would have to pick up an s minus 1 on top and bottom. And since those have the same denominators, we can add those fractions. This fraction and that fraction have to be equal. We're looking what A and B would make those equal. Since the denominators are equal, then the numerators would have to be equal. And this is the most basic type of partial fraction decomposition we did, where we had linear factors and each of them occurred once. And when that was the case, that was a shortcut. We could substitute specific values for our variable n to make some of our terms go away, and we could solve for our other value. So if we put in a -1 for s, this term would go away. That would be -2 times b. So that would be make b -2. If we put in a 1 for s, that term would go away. We would have a 4 on the left. We would have 2 times a. So a would be 2. So that would come out to make our decomposition 2s minus 1 minus 2s plus 1. So that's just rewriting 4 over s squared minus 1, or 4 over s minus 1 s plus 1. This is something that we can translate, or we can do our inverse Laplace for. For the first one, we can pull a 2 out front, and if it was just 1 over s, remember 1 over s, that's just the translation of, or that comes from transforming the number 1. So if we take 1 over s and inverse Laplace it, that goes back to 1. Except instead of having just s, we have s minus a. So we're having not just 1, but 1 times e to the at. So for this one, our a is 1, so 1t. Now, we could really omit this part because they do say if we have just e to the at, that transforms into 1 over s minus a. So that's what we had. So yes, what I said here is okay. We could think about it as that transforming back to a constant, but then this, since we have something added or subtracted to it, that being a translation, so we need the e, or we could think about it as just e directly. For this next one, we have minus 2. If this is s minus a would be -1. So this would be, if it's s minus a, that goes back to e to the a t. So we have 2 e to the t minus e to the minus t. So to get to that, we had, remember, we had to do invert or partial fractions to get to this point. So that's one thing we want to look for. If our denominators will factor, then we're not going to have to worry about completing the square. We can decompose it into separate fractions. But we have to remember that it's not always as straightforward as that one. Let's take a look at this one. No, that's not the one I want to do. I'm sorry. That had something else. Let's do, this is what I want to do. If we have a repeated factor on bottom, then we have to have that factor to each power that we could possibly have from here down to 1. So we could have s plus 1 twice, or we could have s plus 1 once. If this was s plus 1 cubed, we would have to have third, second, and first powers. But here, since it's squared, we include that to the second, and we include it to the first. Our other factor only occurs once, so we have that factor, or that fraction, one time. Since this doesn't matter which order we put our letters in, so since this is s to the first, then we would just have a constant on top. Since this is s to the first, we would have just a constant on top, because remember, these have to be proper fractions. Proper fractions have a lower degree on top. So if this is s to the first, we would want no s's on top. Even though if we multiply this out, we would have an s squared. The factor itself is linear, so we will want to have a smaller degree than the base factor on top. So if that's s to the first in this factor, then we would have no s's on top, so just a constant. So our common denominator is going to be s times s plus 1 squared. This first fraction, to get that common denominator, would have to pick up an s on top and bottom. This next fraction would have to pick up an s plus 1, so that we have an s plus 1 squared. This doesn't have just an s, so it would have to pick up an s also. So if you imagine that fraction and that one are equivalent. If you were to reduce, the s's would cancel, the s plus 1 would cancel one of those, and that would be equivalent. And then this last fraction, it has the s on bottom already, but it needs an s plus 1 squared, so we would have to pick that up on bottom, which means we would pick it up on top as well. Now, this one is not going to be as trivial as the previous example because of this square. If we picked s to be -1, these would both cancel, and we could find c. If we picked s to be 0, these would both cancel, and we could find a. But how do you find b? If we make s go away, that's gone. If we make s plus 1 go away, that's gone. So there are a couple of different approaches that we could do, but one of the traditional ways to do it is to multiply all that out and combine like terms. So we have a cs, we have a bs squared plus a bs. If we square that, we would have s squared plus 2s plus 1. So we would have an as squared, a 2as, and an a. So if these fractions are to equal, the numerators have to equal. So we know how many s squareds we have on the left. We have -2s squareds. On the right, we have bs squareds and as squareds, or a plus b. That's how many s squareds we have. On the left, we know we have -3s's. On the right, we have cs's. We have bs's. And we have 2as's. On the left side, we have a constant of -2. On the right side, our only constant is a. So we know what a is. A is -2. We can substitute that into here. If a is -2, then -2 is -2 plus b. Move that to the other side. So we would get that b is 0. And then to get c, we could plug it in here. 2 a's, so 2 -2's, plus b plus c is -3. Add 4 to both sides, and c would have to be 1. So now that we have A, B, and C, we can rewrite this. So we have A over S, B over, doesn't matter what B is over because B is 0. And then we have C over S plus 1 squared. So our original problem here that we would want to transform, that's too messy to transform in its current situation. It doesn't look like any of our transformations or inverse transformations. So we can do partial fraction decomposition to rewrite it into something that hopefully we can figure out how to transform. So let's start with the first one. -2 we can pull out front. And if we transform 1 over s, remember 1 over s came from transforming 1. So 1 over s transforms back into 1. So that takes care of that one. If we look at the next one, remember when we have s plus or minus something, that's often s minus a, so that's s minus -1, s minus a. So if we imagine how s squared would translate or transform, then we put the e to the at, and that takes care of that translation. So how does 1 over s squared transform? If we go back to our list, let's see, we have s to a power. That looks to go with that one. So how are we going to do that? So t to the n transforms into n factorial over s to the n plus 1. So if we're transforming that, n plus 1 is 2. This and that correspond. So that means n is 1. That means we would need 1 factorial on top. Well, 1 is 1 factorial. So that's n over s to the n plus 1. So that transforms into t to the n. Since we have instead of just s, we have s plus 1, we pick up an e to the at. In this case, a is -1. So we have an e to the -1t times t. Or sometimes you write that t e to the -t. So that last part was a little confusing, so let's say that again. 1 over s plus 1 squared transforms the same way as 1 over s squared. We just pick up the translation from e to the -t. Because if we have s plus a number or s minus a number, we're going to have an e to the at, so we need to find a. So if we rewrite that as s minus something, it would be s minus -1. So that's our a. So that's what we put in as our translation part. And then we have to figure out, well, how does 1 over s squared go? So we want to rewrite this to make it fit our formula. So if it's s squared on bottom, then n would be 1. So if n is 1, we would need 1 factorial on top, and we have 1 factorial on top. 1 factorial is 1. So 1s squared, that transforms back to t to the n, where n is 1. So if we have a number factorial on top, s to that same number plus 1, that transforms back to t to whatever that number is. So t to the first. So there'll be several similar to this. One thing I want to mention, and I'm not going to work tons and tons, but another thing to mention is that if we have something such as an s plus 1, an s squared minus, let's say, minus 2s plus 5 on bottom, this doesn't factor down any farther. If it did factor, we would want to break it down farther to find out what our denominators need to be. But since that doesn't break down anymore, then our denominators are going to be s plus 1 and that full thing, s squared minus 2s plus 5. This factor is linear, so it only needs a constant on top. But this factor is quadratic, so to be an improper fraction, it could have an s, so we need to know, well, how many s's do we need? And it could have a constant. We wouldn't have an s squared because those would be the same degree and it would be improper, but we subtract 1 from this exponent, and that tells us what degree we would need on top as our largest power. So we would s squared here, we would need s to the first, and then every power or every degree down to 0. Let's see. Right. So we would do this one the same way. I don't have a numerator here, so we're not going to work this one all the way out. But we would combine these so that this fraction and this combination would have the same denominator, and then we would set our numerators equal, find a, b, and c. And then once we found out what these are, then we would do our transformations on them.